Welcome to the story of the alum part 3. In an effort to have my crystal grow better, I took it to a warmer place, farther away from the window but with access to sunlight to let it evaporate. And as said in the previous video, the cold caused the solution to contract and trap impurities, diminishing the uniformity of the crystal and making it into small pieces instead of one big healthy crystal. But unfortunately, even though I changed the temperature in the room, which the air conditioner was much colder in the previous weeks, to a warmer temperature during these weeks, there was no change in the growth of like one large crystal, and instead a lot of small crystals continue piling up at the bottom, and a lot of liquid has evaporated, but not much of the crystal has grown. So using what I know about crystal growth and equilibria, I can state that Le Chatelier's principle said that when disturbed, a system will shift in order to reattain equilibrium, which occurs when the rates of the forward and reverse reactions are equal. So a system works to counteract the change that has occurred. And using this notion, I would ensure firstly that I have a saturated solution of alum, and this saturated solution would have more aqueous ions of the reactants that would form the alum than the alum itself. This higher concentration of the reactants would result in a lower Q value, making the system shift towards the products, forming more alum to achieve equilibrium. And to use this concept fully, I would make a seed crystal, which is just one alum crystal formed from a solution, and place it on a string inside of another saturated solution. And so as the solution evaporates, the ions, the system will react to counteract the excess of reactant and will form more product, which is the alum. And attaching the seed crystal on a string would favor one giant high quality crystal, because it would allow more surface area for the crystal to grow and attach to an existing surface. And I would also place it in an undisturbed and warmer location and be patient for it to grow slowly, which is a key factor in ensuring a high quality crystal, because equilibrium is able to fix any potential defects while still in growth if it grows slowly and if it evaporates slowly. Comparing this to my methods and results, I did attempt to have as much of a saturated solution as possible, as I dissolved all of the alum into the solution, and I used vacuum filtration to ensure that all was dissolved and there was none left in the bottom. But on the other hand, my crystal grew on the surface of the vial instead of on a string, and my vial was in the same surface that was shaking, and as that was my air conditioner surface, and that would cause more sites for nucleation, favoring little small crystals on the bottom instead of one big healthy crystal. And in talking about crystals, we cannot forget to mention despacing, as despacing is a powerful tool that lets us reconstruct crystals by knowing their periodicity, which is a small atomic scale pattern that repeats itself over and over and over in crystals in every directions of the atoms. So despacing allows us to recreate the atomic arrangement of crystals quickly and efficiently by giving us quantitative data of where the atoms are and how far apart they are from each other. And so the significance of despacing was that it was the first compelling evidence found for the periodic atomic structure of crystals, which had been hypothesized years earlier, but there had been no direct evidence. And currently it is used in a variety of identification of periodicity of crystals, and most importantly, in 2012, 100 years after Bragg's law was discovered, after Bragg's law was derived, single atoms were identified in an electron microscope using X-ray diffraction. And so X-ray maps of crystal and Bragg's equation have enabled us to successfully find the positions and the identities of atoms in crystals.
So to calculate despacing, we have the formula 2d sine theta equals n lambda, since the diffraction patterns occur in a regular interval of lambda. So to solve for the diffraction distance, we will use d equals n lambda over 2 sine theta. And we were given already that n equals 1. And from the graph, we can observe the last two details to have our unknowns become knowns in our equation. From our graph, we can see that lambda is this small piece of information over here. Lambda equals 0.15418. And when we look at the graph, we see that the peak wavelength is at 20. The peak intensity is at 20. But then we see that 20 is equal to 2 theta. And if 20 is equal to 2 theta, dividing that by 2 theta actually equals 10. .444.